GYPT-Bundeswettbewerbs. Jetzt im Finale treten 3 Teams gegeneinander an. Ich möchte euch die einmal vorstellen. Diese 3 Teams haben gestern in der Vorrunde im Teamranking die besten Noten bekommen insgesamt. Das sind einmal das Team X-Betrag aus Dachau bei München, aus Mihailo, Nikita und Ajusch. Ja, schon mal einen Applaus für euch, dass ihr so weit geschafft habt. Dann als zweites Team das Team Hessen aus Lörrach, Johann, Till und Jonathan sitzen hier. Und gestern mit den meisten Punkten aus Bayreuth das Team in Nürnberg aus Benjamin, Elisa und Ellen. Die haben jetzt im ersten Fight noch Pause. Sie haben jetzt Ellen gerade alleine gelassen. Du musst kurz den Namen deines Teams erklären, bitte.
Also es wurde gewählt von unserem lieben Niklas. Ich kenne den Kontext selber nicht so ganz, aber es ist so ein Insider, wie ich verstehe.
Okay, dann fragen wir nachher nochmal nach, wenn ihr dran seid. Okay, herzlich willkommen auch an euch. Genau, mal schauen, ob ihr den Platz halten könnt. Sind wir gespannt. Genau, dann im ersten Fight treffen das Team X-Betrag aufeinander gegen das Team Heaven und wir hören das Problem 13 des Singing Ruler. Danach gibt es eine kurze Pause, da wird der Livestream auch pausiert. Dann hören wir die Präsentation zum Thema Magnetic Newton's Cradle vom Team Heaven und das Team in Nürnberg wird zum ersten Mal auf der Bühne sein mit Benjamin Graf. Dann gibt es wieder eine kurze Pause und als letztes treten gegeneinander an. Es präsentiert Alan das Problem Electrical Damping und Nikita wird opponieren. So, das sind die Teilnehmenden. Dann würde ich übergeben an Carina Karnitz. Carina Karnitz schert das Finale. Sie wird selbst nicht abstimmen, also nicht voten. Genau, Carina ist selbst teilnehmend gewesen, hat es zweimal bis zum GYPT geschafft. Einmal sogar Gold geholt dabei, genau, und ist deswegen bestens dafür geeignet, Chair zu sein. Ich übergebe dir das Wort.
Okay, so now it's also time to switch to English because that's the official language of the fight. So welcome everyone from my side, now in English. Before heading into the fight and introducing the jury, I have one very important announcement. So for how this match will look like, we will have a 12-minute presentation, a 2-minute break, then we will have a 12-minute discussion, and then we have questions from the jury and grading and feedback. And during these 2-minute breaks, it's extremely important to stay quiet because the teams have to be extremely focused to find their questions, to figure out what they want to ask. And also the jury needs fullest concentration to make the grading. So please, please, please don't start talking in this break. It's really, really important. Also while we are grading. We have breaks in between all the matches where you can discuss what you have just seen. Please, please, not during the fight. It's super important. Okay, thank you. And so with that announcement, I think we can start into introducing our jury. And I would ask the jurors to just introduce them quickly themselves going down the line.
Okay, hi. My name is Ender Kayal. Can you hear me? Okay, my name is Ender Kayal from the Schülerforschungszentrum Hameln-Pyrmont. Okay. Now you can hear me. Well, I start again. So my name is Ender Kayali from the Schülerforschungszentrum Hameln-Pyrmont. I'm a physics math teacher.
Hello, I'm Ilya Götl. I'm not a teacher, not a former participant, maybe the only one, not in those two groups. Just a random guy who thinks about physics. Good morning, everybody. My name is Christian Beck. I'm a math and physics teacher, and I'm head of the GYPT Center in Papenburg.
Good morning also from my side. I'm Thomas Kaiser from Jena. I'm a physicist, worked a long time for the university, and now I'm in the German Patent and Trademark Office.
Yeah, good morning as well. My name is Antonia Macha. I myself am a former participant and am now studying physics as well.
Good morning, my name is Elke Kunert. I'm also from Berlin, but I'm a mathematics and physics teacher, not a participant, former participant.
Hi, Sami Razum, as well a teacher for math and physics from Bochum. Hi, my name is Maxim Walter. I was a participant in GYPT and IYPT myself, and I'm now studying mechatronics engineering in Hamburg.
My name is Jonas Kalvam. I'm also a physics and math teacher.
So, good morning, everyone. My name is Felix Bolling. I am a teacher from Königs Wusterhausen for physics, mathematics, and astronomy.
Good morning, my name is Angela Vösel. I'm an academic at Erlangen University and head of the Erlangen Schülerforschungszentrum.
Okay, thank you very much. So that's our jury for the match today. So now it's really time to start the match, and so I will ask our clock assistant to start the preparation time for the presentation.
Just to confirm, everyone can hear me at the back? Awesome. So I can start anytime, right? Awesome. Hi, good morning, everyone. I am Ayush Yadav from Team X, and as you can see for the last 2 minutes, I'm going to be presenting problem number 13, the singing ruler. The task statement is as follows. When a ruler is clamped at one end and struck, it oscillates and emits a characteristic sound. We're supposed to investigate how the sound depends on relevant parameters. A short phenomenon demonstration. Oh, it didn't play. And you also maybe heard it from my teammate over here. Let's first start with the task interpretation. So we have a ruler with some properties, more importantly the length and some material properties, like the stiffness, for example, which is clamped. After clamping it, we have some kind of striking on it, which is just understood as some downward force at the end, which then gives us the initial deflection and also our release, which then allows it to oscillate in this up and down motion over time, which is like a wave, and then it also gives you the characteristic sound. We're going to define the characteristic sound in a bit in the basic explanation. So let's move on to that. I'm sorry for the slides being, yeah. So we are going to assume that we have a cantilever beam, and we can do this because the task states the beam is clamped, and this beam is then deflected by a bit using our initial deflection or the force we apply on it to strike it. This entire system can be modeled using Euler-Bernoulli. And here, of course, we're going to explain it in detail in the theory, but the main part you need to understand is you have one term, which is the acceleration, and the other term being the elasticity or the bending. And what this does is, if you look here for a second, you can imagine the ruler, when being released, it wants to go back to the initial position because of this elasticity or the hardness of the ruler. But because the ruler has a mass, it continues. It has some inertia, and it continues moving in this direction, and then you keep having these oscillations due to this up and down movement, which is also seen in this animation right here. Let's talk a bit more about the characteristic sound. So of course we need some kind of hypothesis to know what it sounds like. You heard it at the beginning, and the first hypothesis we're going to make is that maybe the overtones are inharmonic. And just to compare it to maybe a harmonic oscillator, what that sounds like, a guitar string, for example. I hope you heard that right now. Yeah. So this is our first hypothesis. We're going to investigate that later. The second hypothesis, just qualitatively guessed, is going to be that the higher frequencies decay faster. Oh. Yeah, the clicker is not that good. Yeah. The higher frequencies decay faster than the lower ones, which gives us the characteristic twang. at the beginning. To investigate this, let's move on to our experiment. First of all, I have a really basic setup to look if my hypotheses are correct, if I'm moving in the right direction, then we'll move on to a more sophisticated one. For the basic setup, I just had a ruler clamped on a table and then another ruler perpendicular to it so that I, when deflecting with my hand, don't deflect it too much. This was just recorded using an iPhone. I also tried to make it a little bit better using a 3D printer head instead and an electromagnetic clamp on a steel ruler to clamp it better and then make it a bit more accurate. It looks accurate, but in reality, this setup was not accurate at all and also not reliable. Nevertheless, we were able to fulfill our initial goal, which was to confirm the hypothesis at the beginning, at least qualitatively, so that we can describe the characteristic sound. And we're going to look at this a little bit more detail right now. Here you can see two different spectrograms of metal ruler vibrating at 1 centimeter deflection and 2 centimeter deflection over there. And the main thing we see here is that the deflection only seems to affect the volume. So if you look at the frequencies, they're not shifted up or down. It's just the loudness, and it's also fairly logical, right? If you move the ruler more, it's going to be louder than if you move it less. Moving on, the inharmonic overtones are there. If you look at the FFT on this side, you can see the spacing between each overtone changes, the ratios change, and are not similar or same every time as in the guitar we compared it to, which is, again, a harmonic oscillator because it is a string. And at the very least, the higher frequencies decay faster. As you can see here, maybe we look at 4,000 hertz, it's gone after 0.3 seconds, and the lower frequencies stay on for 1.2 seconds. So this is also confirmed from the basic explanation. Moving on to the more sophisticated experimental setup, because of course it's GYPT. It looks quite complicated, so let's go through it step by step. You have this ruler again. This is clamped, and by the way, it's really important to ensure that it's clamped at the edge of the table or clamped really well, because again, we're assuming a cantilever beam, and more to what happens if it's not clamped good in the appendix sometime later, maybe for the discussion. So it's clamped, and then to do the deflection, I have two motorized linear rails. Using my Raspberry Pi setup, I could move them with an accuracy of about 0.5 millimeters. I also made a metal edge to do the actual pushing and the deflection itself. This was then measured using a pre-calibrated UMIC-1 microphone, which is used for these kind of scientific measurements. This entire experimental setup was enclosed in styrofoam and acoustic foam so that I can minimize any reflections, harmonics, or resonances. Let's see what the results look like. So for the plastic beam swinging, or the plastic ruler swinging, here you can see on the y-axis the frequencies, and on the x-axis the length, and also the frequency we measured for each mode of vibration. So the fundamental mode, the one you hear the most, F1, the second mode of vibration, and the third mode of vibration, and as you can actually not see because the standard deviation is so small, we had a pretty accurate setup or measurement over, I think, 5 or 10 iterations for each length. Why did this skip? Moving on to the length and frequency relation here for a steel ruler, you can again see that we have a pretty small standard deviation and maybe also more measurement points here with the steel ruler. And again, for the steel ruler, we can also look at the different modes of vibration which we measured here. Pretty much the same to the plastic ruler. To explain all of these measurements, and maybe also later look at more of them, we're going to now move to the theory. The theory is structured as follows. First, I'll explain to you the beam equation solution. Then we'll talk about, then we'll talk about the frequencies and modes, the dampening, of course, and at the end, full solution with also a comparison. Now, for this theory, we have some we have main assumptions. First of all, the cantilever beam, as I talked about at the beginning. Then the length being greater than the thickness, and this is given because we have a beam. The cross-sectional area remains plane and perpendicular to the neutral axis after bending. Sounds complicated, but this just means after bending the ruler, it returns to the normal position and is not permanently bent or something like that. And no shear deformation, and that the material is linear, elastic, and homogeneous. And this is also one of the reasons why wood is maybe not the best option to look at, but more to that later. So first, the Euler-Bernoulli beam solution. We have to understand it first. So here in the material part of this equation, you can see that we have the Young's modulus and the flexural rigidity, so to speak, of the material. This is the spatial term which gives you later the mode shapes. it's just the restoring force per unit mass due to bending stiffness, and the first term is just the acceleration term. It just gives you the local acceleration of the beam. To solve it analytically, we do a separation of variables, get a temporal and spatial equation, and we're going to move forward with the spatial one to get a characteristic equation to tell us what the modes are like. Plugging in the boundary conditions, because of course we have a cantilever beam, there's not going to be any displacement or rotation at the fixed end. We also have boundary conditions for the free end. We get this characteristic equation, which then gives us the mode the mode numbers and the wave numbers. And here we can again see what we presumed or maybe had in the hypothesis. It is actually inharmonic, and you can also see the mode shapes here. Moving on, the dampening. Of course, our ruler is not going to be oscillating forever, right? So here we have just exponential dampening with a quality factor Q, which you can get literature values for or fit for and see what it is experimentally. And here again, you can see it's supposed to be, this is the theory, it's supposed to be exponential because when you do a logarithmic scale, it's straight lines. Let's compare now our theory to, first we have the full model. Of course, it's just the time response for each mode with the decay, the oscillation, and the shape. And then the complete solution is just the sum of all of these modes. So you have this kind of superposition at the end. With this, we get the animation we saw at the beginning, or the simulation we got at the beginning. We can also look at the modal amplitude decay over time. We can also simulate FFTs. That was last slide. And here we get a fairly complicated overview of all the parameter proportionalities. In the first row, you have the parameter to the mode 1 frequency. In the second row, you have parameters to the mode 1 decay time. And the first column is length, thickness, Young's modulus, and density. And as you'll see, Young's modulus, density, and thickness, these are mostly, not thickness, but Young's modulus and density, they are inherent material properties. So it's quite hard to experiment independently for them, to change them independently. And one of the most important things we're going to be looking at is then the length. For the theory experiment comparison, I got for each recording FFT power spectrogram, FFT and the experimental FFT, where I overlaid the experimental or the theoretical values. I also got an energy decay analysis, which I made it a bit easier for me to look at the dampening because I used the normalized amplitude instead of decibels, because decibels is quite complicated then. And also we get the measured vibration of each mode and the theoretical vibration of each mode compared over there. Let's look at the entire batch. Here we have a batch summary of a steel ruler with 9 centimeters of length. And then we do it, iterate over it 5 times. The theoretical values you can see with the squares. And you can see it's quite a good match, I would say, with the experiment which we have here. If we linearize this relation using not the mode numbers, but lambda n squared, the wave number squared, you can see it's a straight line, and again, a good match. Then we can also look at the plastic ruler. We again here get a really good match. Linearized, it is also a straight line, so our theory is correct. And here we can also see all of the measurements together, linearized, and yeah, it is still a really good match which we have here. Moving on, the relation of the free length to the frequency, you can see the theoretical values we should be getting, and each individual measured, or not, the mean of each individual measured experiment. It is, again, a good fit, I would say. Of course, we have some deviations, but they are, in the end, yeah, minimal, I would say, because no experiment is really perfect. Here you can see for the different modes. Here you can see it linearized using a log-log scale. And then here, all the modes for the plastic and steel ruler together. That was all. I could say that it was a very good fit in total. And to summarize, we had made the task easier using the task interpretation and a basic explanation. We constructed an experimental setup which was quite sophisticated. And with enough experimental results and a full model, we were able to get a good comparison and good fit. That's all. Thanks a lot.
Thank you. Now 2 minutes preparation time.
I'm ready for you to start the clock. Yeah. Okay. Well, thank you for your very interesting presentation. I liked it a lot. It went into detail quite well, but obviously I still have some questions left. Let's go back to the task first. First of all. So the task reads that if a ruler is struck, right?
Yeah.
How would you say are struck and displaced equivalent, and how are they different? Because in your setup, you clearly used something not like a ball to let it fall down, obviously, but a displacement mechanism.
Good question. I actually have that in my appendix, and I'll start explaining while I actually click through the slide. So of course there's a difference between when you strike it with something and when you deflect it. When you deflect it, you just have the... oh, sorry. I exited out of the presentation. Wait a second. Right here. Okay. So here you still have the similar amount, the similar equation, but the contribution of each mode is no longer dependent on the frequency itself, but it's the strike strength and how well or where you actually strike on the ruler.
Okay, I would agree with you on that. Okay. So then let's go one slide further after the task after the task, because I was missing definitions. What do you define as sound? Because first of all, we would need to look at sound. Yeah. We need to know what sound is.
Yeah, so I simplified the experiment a little bit, saying that the sound we are hearing from we are measuring is just going to be similar or exactly same to the oscillation of the ruler. This is not quite accurate, as I think you're going to point out right now, because we have to look at the sound radiation of the beam.
Yes, I would quite actually disagree with you on that, that they are not even slightly similar, but completely different. Okay. Because in air, pressure differences cause sound. Pressure differences are what we hear or what we perceive. So I would have liked you to define that maybe more clearly.
But again, I wouldn't say it's quite different. I agree that I should have looked into it. But again, you can just take, so you have the normalized velocity of the ruler, and you assume that it's a point dipole, and then you get, I think it's going to be pretty similar. Yeah.
And one more thing, what do you define as a ruler? Because this one, how long should it be? What is the boundaries of that boundary condition?
Yeah, so ruler, to make some boundaries, so something normal like a ruler, some kind of beam. Of course, it's not supposed to be too thick, because then you don't have a beam anymore. So yeah, and it's not supposed to be too short, because if it's too short, then you have to use Timoshenko at some point.
Okay, okay. Then would you say if the ruler is too short, does it resemble rather a plate oscillator, for example?
Could be. I did not look into it, because too short would be then going into, as I said, Timoshenko, and then it's, it's supposed to be normally around some order of magnitude greater than the width.
So for your basic explanation, I think I didn't quite get where the sound wave originates from. Would you say there's a specific point on your linear, like for example, or on your ruler, for example, where you strike it or anything?
So of course, this is the point you made at the beginning, right? So what I'm doing in my simplification is I'm looking at the superposition of all of the modes, and then you say, okay, there's a point at the end which is vibrating, and that gives you the sound, which is not quite accurate, because in reality you have the entire beam which is moving and then giving you this,
Yes, okay. I like that you pointed that out. So yeah, then let's move on to your setup.
Okay. The basic one or the more sophisticated one?
Let's just go to the more sophisticated one, where we see the entire sketch and whatnot. Right there. One thing I would like to point out is, that microphone that was always positioned at the top?
Yeah, at the same, it was the same amount of distance away from the edge always.
Okay, then would you expect differences in your frequencies, for example, in amplitudes, if you position it differently?
Yes, of course. So because it was same here, I ignored it for the moment. But if you look at, for example, if the ruler if the microphone was placed in this area, you gotta look at it a bit more complicated, right? Because if it was just a ruler in like free space.
Sorry,
Yeah.
I don't think it's that complicated because, well, if you look at that ruler and you go up, you go down, and if you place it in that plane, then pressure, high pressure, high pressure, high pressure, double the frequency. That's my intuitive explanation.
That would be true, but you have, so I expected that the sound would be similar, not the same. The loudness would especially be different depending on the distance, but similar because you have this enclosure and then it's going to vibrate around, and yeah.
Okay, so also for your geometry, did you include any correction for that in your theoretical model? For example, like you mentioned that the distance between microphone and ruler was constant, but did you include that?
No, I don't get what you mean, but okay.
Okay. No, because distribution of waves happen through air and how long it takes for you to...
Yeah, as I said, it was at the same position all the time, so yeah.
Okay. One suggestion I would make to you to maybe even improve that setup is to add a new characterization, maybe amplitudes. Because if we, for example, take a laser measurement and put it somewhere on the ruler, I don't really know where, or I wouldn't suggest you. So we put that there, and then we can note down the distances each and every time frame, and you have a new characterization, right?
That is true, and I think it's also a really good suggestion because it's then easier than just measuring the loudness of the sound.
Yes.
Then you get the amplitude.
Indeed.
So, yeah,
Yes.
so a good suggestion.
And one more suggestion with that, you could vary that, right? You could vary the position on top of the ruler. So if you imagine the ruler right there and the laser pointer right here,
and
you could vary that, right? And frequencies or maybe your harmonics have knots, right?
Yeah.
These knots can be found out, right? Through that measurement. Because if you were to put this laser measurement on top of right on top of the knot of a frequency, then you would not read that frequency, right?
True, but I don't really see why you would need to do that, because if we can say that the modes are visible and you can see that they are there, then you can just fairly assume that they are going to be there at the position. I don't see the extra information we're gaining by doing this.
I see an experimental result that
you see that the knot is there where...
You can calculate those points, of course.
Sure, yeah.
But you can also measure them, and that was one suggestion.
Yeah.
Well, let's go a bit back to one of your animations, I think. The very first one you showed.
You mean...
Yes,
that
right
one.
there.
Yeah.
One more.
Yeah.
Okay.
Yes.
And could you go back to the slide and just cover just for the front to see the title or the screen? No, sorry.
Do you have slide numbers maybe?
No, the same slide, but
the same slide?
I want to see the first frame of
first frame
animation.
That is going to be difficult to do, but okay.
Yes, but we see, right there. I didn't know if you catch it, but the ruler was quite deformed, right? And I would really like to see an image of a ruler that would bend like this, because I don't expect anything to behave like this in our
Yeah, so in reality, you would have to do some finite element simulation of this, but of course, I tried to do it. I did not have any Windows computer powerful enough to do this, so this is just some trivialized try in Python. So of course it's not accurate, but it shows you what.
I think one thing you may correct, because to me it looks like that. Maybe some of your modes are more dominant than they should be, because if you compare a higher, you have way higher amplitudes and way higher frequency on your first harmonic or on your bass. Then on all the other modes on top, right? Yeah. And I think because the simulation shows that, because the other modes are too dominant. Do you get me?
Maybe, yeah, but again, the simulation wasn't the main part of my experiment, right? Later, if you saw the dampening, I think it was quite okay then.
Of course.
Yeah.
So let's go. Let's jump to your plots.
Yeah.
I think that was slide 44. I
Slide
don't quite
44.
remember.
Yeah. I'll just jump to it.
Okay. Well,
Here.
you see, sorry, wrong slide. Maybe go back a bit. Yes, that.
This
right
one?
there.
Yeah.
Nope. One more. Yes,
Okay.
right there. Why do you think you have such a stark disagreement between theory and experiment on top?
Yeah. So I think the amplitude for the modes are okay. But here you have a strong disagreement because, again, this normalized amplitude I'm taking, it's not of just the modes, which I'm theoretically calculating, it's of the entire sound. And of course you have some harmonics, some resonances, and that's why it is wrong over here. And at the end, it's a little bit more wrong because the microphone also has some kind of automatic gain. Yeah.
Of course. And one more thing I want to mention on that slide, you say you pick your errors quite inconsistently, but on that slide you see an error of 7.6% on your first frequency.
Yeah,
Why
but this
do
is
you think is that?
This is just one experiment, and as you can see, it is a lower frequency, 42, 43 hertz,
Yes.
and the setup, it just resonates with it. So this is something I could improve on.
So maybe you could just measure more?
That's what I did. So this is just one experiment. Okay. And later I've shown you the mean of 5 to 10 experiments. So this is why the error is
yes,
big
yes,
here.
yes, I remember. Okay, well then I think we've almost run out of time. So I would like to sum up our discussion. I've made some suggestions to maybe further improve your setup, and we've discussed some discrepancies between my point of view and yours. So thank you for your discussion, and that was my part.
Thank you for your suggestions.
Okay, so we head straight into jury questions. Who wants to start? Yeah, Antonia.
Could you maybe go back to slide 29 where you did the dampening?
Yeah.
So my question would be, you showed quite a different range of cases for the decay. Did you use these exact cases for your measurements? And if so, did you do any independent measurements to match them exactly to your experiments?
No,
or are these fits?
For dampening, I was not able to do this. I, of course, tried it sometimes, but it was not that accurate, as I told you, because of the normalized amplitude and the harmonics. But this is something I'm looking to improve in the future.
Okay, so later then for the decay plots, were these then fitted, or?
It's fitted, but I get similar results to what I would expect. So for like plastic.
So the trend is the same, basically. Okay,
sure? Yeah,
that's fine. Thank you.
Okay, next question. Christian.
We're talking about the clamping, and to the reporter, you said that you clamped the ruler on the edge of the table. What would you expect to happen if you clamp it more onto the table?
That is a really nice question. So what happens is you have this kind of interaction. So I don't know if you can see it here. If you have this ruler, and it's in the moment it's bent upwards. So you have still the normal cantilever, which we can approximate here. But when it's bending down and it hits the edge, you kind of get like a free beam, which is getting hit in the middle, and also like a cantilever beam here. So it then all adds up. So it's quite complicated then, and yeah, it gets unpredictable after some time.
Okay, more questions. Yeah, Maxime.
To the reporter, you mentioned you disregarded wood as a material. Why?
Because if you look over here, wood is not homogeneous. It is, yeah, it has these strands in between, and you could expect that it also gets bent easily after some time or breaks in the middle. And to bend wood, my setup is not strong enough because I use a styropor box, and it takes a lot of force to bend it. At some point, it would go away. I did try it once. I also got it to work once, but it's not that reproducible.
Okay, quick follow-up to the opponent. Which property of wood do you believe the reporter is referring to when he mentions it would work as well? And do you believe the same phenomenon could be observed?
I think, for example, the stiffness of wood is might be a problem, but also, for example, inconsistencies with other materials, like E modulus or the Young's modulus he mentioned, I think wood has quite a large range of that, so measuring that and determining that would be very difficult.
I think there was a question with Sami. No. Okay, then Antonia again.
Just short, because there was a discussion about the beam profile. Did you compare your actual observed beam profile to your predicted one based on the theory?
Beam profile?
The whole bending profile of your deflected beam?
That I did not do, no. So I only looked at the measured audio and not with the camera.
Yeah,
how it's
no worries, thank you.
Okay, there would be the chance for one quite quick question. Yeah, Maxime again.
To the opponent, you used a lot of time talking about laser measurements of the position of the ruler. The task calls for sound parameters. How do these two correlate?
Amplitudes and frequencies all all bunch up in one another, and if we can figure out some amplitudes, we can also then look at frequencies provided by a microphone, for example, and compare those two, and maybe if we have some non-linear effects through too much bend.
Thank you. Sorry to interrupt. Okay, so now we have to finish the grading. We need a couple of minutes. And then for the finale, there's a specialty. So because we are going to hold the grades up. Yesterday, everything was graded in secret. But today, you will directly see what the jurors think of the just seen fight. Okay, so we just finished grading and also the calculation, which is sometimes the hardest part. So now please prepare your marks for the reporter and then hold them up once everyone is prepared. Yeah, okay, looking good. So please hold them up now. We have 8, 8, 8, 8, 9, 8, 8, 9, 8, 8, 9. Pretty uniform. And now for the discussion, we have, please hold them up now. And now we have a 8, 9, 8, 10, 8, 7, 6, 9, 9, 8, 8. So a bit more variety here. And so we will start with some feedbacks now. And for the report, I think it was so uniform. Anyone who wants can just go and give some feedback. Yeah, Maxime.
Thank you very much for your report. You investigated a lot of very interesting characteristics, but I believe you disregarded a lot of potential experiments. Like in all of your mathematical models, you talked about Young's modulus, the moment of inertia, the cross-sectional area, and you basically completely disregarded all of this parameter variation and just used some arbitrary steel and some arbitrary plastic. So there could have been a lot more experimental data, but the stuff you did show us on experimental data, especially with all of the modes, it just fit very well and was very enjoyable. Thank you.
Okay, anyone has an addition to the reporter? Okay, then we will move on for the discussion, and maybe Sami can give a comment on his 6.
Okay. First of all, thank you very much for this nice discussion. I gave the lowest grading. You started with some strong points that really caught my attention. You kind of lost me sometimes, though. You started off by criticizing him for simplifying it by looking at the oscillation and not really looking at the sound. And then you started your own suggestion by using a laser and quantitatively describing that, and I thought that didn't match over. Stick to the sound. What do you think? What kind of what's it called? Improvements would you do to really focus on the sound? And you brought up other points, but I really thought those are great. Stick to those, and then you switch to something different, and that's why I gave the lower rating. The physics was perfect, but I think the structure didn't match for me. I'm sorry. I'm really sorry.
Okay, and then Thomas with his 10.
Okay, I had the quite opposite impression. Yeah, so opinions are different. So you had a very hard time because it was an excellent talk. Yeah, I was really thinking like, oh, how to post this. But you really talked about all the interesting points that I had on my sheet. I wanted to ask myself. And you made up more points. For example, the question how the sound is actually generated. I found this very relevant. And your suggestion to improve the measurements, which are already very, very good with the microphone, with this kind of laser type optical setup, this really excited me. So, and this is why I think this was a perfect opposition. But opinions are different.
Okay, so thank you to both teams. Now we will head into a short break, and before we do so, please remember to give back your USB keys to where you had to sagen, unten kippt sie wahrscheinlicher um als oben. Ja, ja. Okay, so the jury has returned. It is complete. We have our teams ready to go. So the second match of today will be Team Heaven giving the presentation about problem 15, magnetic Newton's cradle. And we will have a discussion by Benjamin Graf from Team Inu in Nürnberg. So let's get started with that second stage. We will start the preparation time now. Get started anytime you want.
So can everyone hear me? Great. So I think I'm ready. So hello everyone and welcome to my solutions about this year's problem number 15, the magnetic Newton's cradle. I'm Jörn Hoffmann from the Phenomenon and let's start with the task. Repulsing and touching magnets are used instead of colliding bonds to make a new type of Newton's cradle. The new cradle can act in a similar way to a regular cradle, but can also exhibit other interesting behavior. Explain and study the movement of the magnetic cradle. So at first, the task tells us that we've taken normal Newton's cradle and then should replace the colliding metal balls with repulsing and touching magnets, so that there's always some space between the magnets. Further on, the task mentions two kinds of motion of this new type of cradle. On the one hand, a rather similar looking motion, for example, if it deflects two other pendulums of the system, and on the other hand, a rather different, interesting looking motion, for example, if we deflect only one pendulum on one side. And after explaining the movement, we should study it on all of our given pendulum properties, as you can see right here, where the movement can be quantified using those methods. Let's go further into the qualitative explanation of the phenomenon. First of all, if we take a normal string pendulum and deflect it with a simple harmonic motion, and since this is just a normal damped oscillator, we also see only one peak in our frequency spectrum, since there's only one normal periodic mode the pendulum can act in. Further on, if we now attach a magnet to that pendulum, then there will be a magnetic field around it. So if we put several of these pendulums next to each other, then deflect the first one, then there will be a force on the second pendulum. So it'll move a bit and also act again a force on the first pendulum. So in this case, there will be a coupling effect of both of our pendulums, and because of this, we'll be able to see two peaks in our frequency spectrums, which are now the two periodic norm modes of our system. Those two norm modes are on the one hand a symmetric mode with in-phase correlation of both pendulums, and on the other hand an antisymmetric mode with anti-phase correlation, where of course the frequency of the periodic motion is higher due to the repulsion. Those norm modes can also be displayed in those mode diagrams, where we plot each of our pendulums above each other, and the color represents the correlation between of our pendulums, where purple represents anti-phase correlation and yellow represents in-phase correlation. Further on, if we now deflect our system in any other ways than those two conditions for the norm modes, then we'll see a so-called decay in our norm modes due to because the starting conditions gets projected onto the shape of our norm modes, which is then called a superposition of those several modes. This is then the explanation where we can see two peaks in our frequency spectrum. However, if we now add more and more pendulums, then there will be also more and more visible frequency peaks due to the higher amount of norm modes, due to the higher amount of degrees of freedom. Let's move on now to my experimental setup, where I'm actually using cable rods to connect my repulsing magnets with here the ball bearings here attached an aluminium bar, where of course the position of our magnets can be easily adjusted, as well as the length of them. Further on, there's some colored points on both sides, which are for video calibration and for correcting all of the relevant optical errors. And before that experimental setup, there's a video camera to film the whole process. Additionally, there's also a start deflection mechanism right here, which is used to control all of our initial starting conditions of our system. So now we built a fully abundant experimental setup, which is used to track our motion, where all of our relevant parameters can be easily adjusted. For the data evaluation, I'm using video tracking using OpenCV, where of course all of our relevant optical errors have been perfectly corrected. Further moving on with my qualitative model of my system, where I'm using a coupled system of equations of motions, where all of our relevant torques are acting on our moment of inertia, which is given due to our pendulum geometry. Further on, there are three different torques acting in our system. On the one hand, there's the gravitational torque, of course, which can also be resolved to this equation. Further on, there's of course the magnetic torque, which is simply the sum of all the magnetic torques from the other magnets. However, we can see in this equation the magnetic force from one pendulum to another is used, so that's where we're going to modulate now my further quantitative model. For doing that, we first, however, need to talk about how to modulate in case of permanent magnets, which is done by the bound surface currents, which can be parameterized as here shown on the right-hand side. And further on, under these conditions, we can then apply the Biot-Savart law on our given parameterization of our magnets, so we can solve the B field of our magnets numerically. However, for doing that, first of all, need to determine our magnetization of our magnets, which got fitted onto the B field data of our magnets, which got measured using a Hall sensor and a robotic arm for precise position controlment. Further on, for now calculating the force between two pendulums, we're calculating the Lorentz force on the bound surface currents due to a magnetic field from another magnet. The last torque that's now missing for our equation of motion is a friction torque, where we have actually two kinds of friction in our system. On the one hand, there's of course a Coulomb friction torque due to the ball bearings, which got fitted onto the trajectory of a free swing pendulum inside a vacuum chamber. And additionally, there's of course also an air friction torque, which can also be resolved to this equation and got also fitted on the trajectory of a free swing pendulum, as you can see right here. Now we have all what we need for solving our equations of motions, which then got done numerically using Runge-Kutta-8 method. However, if we do this and take a look at one example trajectory and the adaptive Fourier transformation, then we can see that there are some distinct peaks in the spectrum. However, we won't get any further information about the exact norm modes or about simple parameter dependencies with the numerical theory. For solving that problem, we developed an advanced analytical theory, which is used to predict all of our frequencies of our system. For doing that, we first are going to cancel out the friction torque, since it's not relevant for the frequencies, and further on, we're going to linearize on the one hand the gravitational torque using the small angular approximation, and the magnetic and the action torque using the dipole approximation. And by assuming that only the nearest neighbors are affecting each other, we can define as a simplified coupling matrix, which then can be put into this linear ODE system second order, where the solutions of the frequencies are well known and can be calculated using this formula. Going into my results, first of all, since the task mentions to compare the movement of the magnetic cradle with the movement of the regular cradle, and it also explicitly mentions a similar way, we first have to characterize what in fact is the movement of a regular cradle. We know that for the regular cradle we have a conservation of momentum, so if we take a look at one example trajectory of this irregular cradle, we can see that there's a periodic motion with one basic frequency. However, if we take a look at one example trajectory of the magnetic cradle, then we can see that in general there's a much more complex motion, as you can see in this trajectory, and additionally, if we take a look at the Fourier transformation of that, then we can see that we can see several of these frequency peaks, which indicates a quasi-periodic motion, which is due to the superposition, which can be linearized displayed with this equation. We also know, as already stated previously, that the mode dominance depends on the initial conditions, since starting deflection gets projected onto the shape of all norm modes, as you can see right here. So the question now is, when can a movement be actually described as similar? We know that for the regular cradle we have a periodic motion, so what we have to do on the one hand is to search for starting geometries, which are only decaying in one or a very low amount of our norm modes, and additionally we have then to check if those norm modes are displaying similar looking motion. For doing that, we have to extract the basic moving patterns of our norm modes, which is mainly defined by our phase differences, which can be extracted using the complex Fourier coefficient, as you can see right here, where we can define as a coupling coefficient, which then can be plotted into those graphs, as I always showed before, for each of our norm modes, for each of our pendulum combinations, where the color represents the correlation, as you can see right here. With that knowledge and with that graphs, we can now make decisions about each of our norm modes and decide with the displaying similar looking motion, where I want to start first of all with the first norm mode, where we can see a full in-phase motion of all of our pendulums, and since this mode is kind of trivial, we can of course also observe it for the regular cradle, since there's no relative movement between the pendulums and also no collisions, so this kind of movement is completely identical. Moving on to the much more interesting second norm mode, where we can see a symmetric motion around the middle pendulum, and also this kind of motion can be achieved kind of similar for our regular cradle, can therefore consider as a cradle-like movement. However, for the other three norm modes, we can see highly more complex motion with high magnetic repulsion, and since for the regular cradle there's at least one possibility for change of phase difference in our system, those kinds of norm modes cannot directly be achieved for a regular cradle. However, what we can still see is that, for example, for the fourth norm mode, as well as we could see before for our second norm mode, we have still this purple diagonal, so as geometrically equivalent pendulum positions are still moving anti-phase. So we can say that also possible superpositions of those norm modes can be quantified as comparable movement and therefore considered as similar due to symmetry. So now we identified three kinds of motion identical equal, like in the comparable movement, which also can be considered as our possible similar way. So now we fully investigated our similar way, and let's move on to the other interesting behavior, which is mainly shaped by the dominance of all of our norm modes. As you can see in this trajectory here, the agreement between our theory and experiments is quite well, and we can also see in our Fourier transformation that now all of our norm modes are dominant. And additionally, if we now plot our analytical frequencies inside of that, we can see that there are, of course, some bigger deviations. However, we can still identify all of our peaks right here. Going into the analysis, first of all, we can see that for the pendulums 1 and 5 and 2 and 4, the shape of our Fourier transformation is nearly identical due to the geometrically equivalent pendulum position. Further on, if we now want to go into the analysis of all of our amplitudes, starting with the first norm mode, where we can see in-phase motion of all of our pendulums, and therefore also the amplitude of all of our pendulums for this norm mode is similar, as we could also see in our viewers previously. Further on, with two other interesting norm modes, which is the second and the fourth norm mode, which are indicating no movement here for the middle pendulum, and also so those norm mode peaks are not dominant for the middle pendulum. Going into a bit more detailed analysis of the movement, where I want to go to the parameter dependence, starting with the distance between the magnets. Here we did peak detection of our frequency spectrums for each of our trajectories, and you can see, so here have all of our 5 norm modes for all of our distances, and generally we can see a decreasement of all of our frequencies beside the lowest natural frequency, and this trend also agrees with our analytical theory, where of course the Dipper approximation of the analytical theory phase for very low distances. Additionally, we can see that there's a convergence proof using the analytical theory, and there's proportionality, which also can be proved. Moving on to another parameter, which is the magnetization, where we can see an opposite trend, and we can also prove that there's a proportionality using the analytical theory, and this convergence towards the natural frequency, since for very low magnetizations, as also before for very high distances, the coupling between the magnets gets lost. Further on with another parameter, which is the length, where we can see, first of all, that our lowest frequency, which is the natural frequency, is decreasing. All of other frequencies are decreasing the same way, so the coupling gets not really affected. What's in fact only changing is the lowest natural frequency. And now to my last parameter, which I want to talk about, which is the number of pendulums. Generally, we can of course see that for more and more pendulums, we have more and more norm modes, so motion will get more and more complex. And additionally, we can also spot a difference between even and odd number of pendulums, since, for example, if we take a look at the second norm mode, there for even number of pendulums, of course, the characteristic type middle pendulum, which is not moving, is of course missing. So now we also fully investigated our other interesting behavior. Coming to the task fulfillment, we fully explained our movement using our theory and our results, and also did a lot of studies on the movement using our abundant experimental setup, and did a lot of investigations on our movement, including our mode diagrams and also possible parameter dependencies. And here I've also a small present for you to always have a souvenir of this fight. Thank you very much. Thank you.
Thank you. So now we have 2 minutes preparation time for the discussion.
much for this interesting report. I think what you did very well. However, in our opinion, you missed some of very interesting physics in this phenomenon. But let's begin with what you did. At first, we can look at the qualitative explanation.
Yeah, sure.
Here, you directly focused on the individual modes. However, in my opinion, the relevant process in this phenomenon is rather the momentum transfer. And I think the qualitative explanation of this transfer of momentum was quite lacking.
So I agree. So you mean the energy transfer between of our pendulums?
Yeah, exactly. You showed it with like two pendulums swinging in phase, but I think this should have been more in-depth for the bigger case.
So I also mentioned the magnetic interaction between our pendulums in one of our slides with the qualitative explanation. So can you please tell me what you would expect there additionally to that to qualitatively understand the phenomenon better?
Yeah, for me, the focus in the beginning was too much on the frequencies, which is, in my opinion, not really a qualitative and basic explanation, but I think that this is just like a general thing of what a qualitative explanation is. So maybe we can just move on.
So can I comment on that? So yeah, you're of course right that the energy transfer and the transmission of the energy is of course very important. However, I disagree to you since the superposition of the modes is the actual explanation why we can see exactly this phenomenon we can also observe in our trajectories and the frequency spectrums, and therefore I would still state that this is a good qualitative explanation.
I agree that the modes are interesting, but not the only interesting thing in this phenomenon. We'll come to this later again. But let's at first begin with your experimental setup. You stated that you had a release mechanism. Does this mean that you do not do your release by hand, or do you release your pendulums by hand?
So I used this release mechanism, which is simply a device for adjusting the angles, the starting angles. And of course, I also used my hands, so I just lift them up and press them against this start deflection mechanism. But I also believe that this is quite reproducible because of this fixement point due to the angle setup. Yeah.
Okay, I agree that this is valid. However, I would like to have mentioned it in the presentation that you deflected by hand and not only by the.
Do you have a better idea how you can?
No, I think that is totally valid. However, for me, it was not clear that you used your hands, so I just wanted to clarify this. Okay, so as a big focus of your presentation was these eigenfrequencies and these modes, let's look at these more in depth. Yep. Could you maybe go to the slide where you determine them theoretically, especially the slide with the moment of inertia? I think it's slide 29.
This slide here?
Yeah, exactly. Here you calculated your moment of inertia. So for this calculation, how do you approximate your pendulum?
Approximate my pendulum with a point mass for the magnet, and then additionally I'm also integrating over the length of the rod to also consider that on the one hand from a moment of inertia, and also in my gravitational term later. Yeah.
Okay, so is this completely theoretically determined, or in any case experimentally fitted?
No, it's completely theoretically determined. So what we have here, we have our mass, which we could simply determine, and our length, and the linear mass density of the rod, and so on. So it's completely calculatable theoretically.
Okay, that's of course very nice. However, I think that the approximation of the point mass and the carbon rod might be a bit too simple. Do you have, and just as a follow-up question to this, do you have any different modes of, moments of inertia that you compare to each other?
So, of course, the moment of inertia would change for different pendulum lengths, which are also variated in my results. However, I would disagree to you that this is a bad approximation, yeah. So I still believe that, especially due to the integration of the rod length, this is quite accurate still. Yeah.
Yeah, I really like that you do respect the rod. However, I think this might have been a bit better. for example, if you deflect the pendulum once, a single swinging pendulum, then you can accurately determine the moment of inertia. But I agree that this is not the biggest point. However, we can see what results out of this theory, of this analytical theory. Could you maybe go to the slide where you show the distance over the mode frequencies?
Yeah, sure.
I think we can see some very interesting behavior of this analytical theory here.
Do you mean the slide?
Yeah, exactly. Well, looking at how this analytical theory compares with the experimentally and numerical results, we can see that for smaller and smaller distances, the two values diverge. What do you think is the reason for this?
So I think the reason for that is the Dipole approximation, since we can see that our numerical theory is fitting very much better to our experiments, as you can see right here. And the Dipole approximation is a far field approximation. So if we would decrease the distance, then the deviations would get more and more stronger, as we can see also right here.
So you would say that for a distance of 8 centimeters, a dipole approximation is not valid?
So that is just a distance between of the fixed points of the pendulums. Of course, the magnets can still move a bit more closely during the movement of them. So I would say that this is the explanation for this deviance of the analytical solution. Yeah.
However, your analytical solution only covers small variations from the resting position. So the magnets do not get too close to each other. So in my opinion, I think that this is not really the case why the analytical theory breaks here. What is, in my opinion, more relevant is when you're looking at this, we get smaller and smaller distances. The outer pendula get more and more deflected. Do you agree?
What do you mean? Can you explain it again? That?
Okay, so at first, for very large distances, the resting position of each pendulum is straight downwards.
Yeah, that's correct.
Of course. And if we now approach smaller and smaller distances, the resting position gets increased more and more.
Ah, yeah, okay.
Yeah, of course. And then you stated for your analytical theory, you linearize the equations of motion.
Yeah.
Around which point do you linearize these equations?
I linearized them around the equilibrium position. So we assumed that there's some equilibrium position, which was done using our the Dipole approximation and so on. So I want to see more details about the analytical solution.
We can just quickly go back to your derivation where you linearized especially the gravity. Could you maybe show this again?
The linearization?
Linearization of the gravity.
Yeah, sure. I think that's somewhere... Ah, yeah, here. No, sorry. Here.
Okay, so am I right that for the gravity, there is no, for the linearization of the gravity, there's no consideration of the magnetic torque? Am I right there?
For the gravitational torque, yeah, of course.
Okay, but now, as you've agreed, the equilibrium position around which we linearize is not the one that goes straightly downwards. And you said that you considered this equilibrium position in your linearization. But for the equilibrium position, do we not need the magnetic moment?
So, yeah, I understand your point. Of course, there are some deviations of the analytical theory, and we need to make a lot of simplifications and assumptions for even solving that complex problem analytically. So I definitely got your point that there are, of course, some problems, and you can also see that the analytical solution is fitting not so good than the numerical simulation. So, but I think that's just need to solve the problem analytically.
Yeah, but in my opinion, I would propose here, as you're linearizing around the equilibrium position, this is not the sinus here, where you can really do the small angle approximation. It's rather somewhere here, and then you really have to take into account for the gravitational torque to this equilibrium position and thus the magnetic torque. I would think that this would greatly improve your analytical theory.
So,
however,
Can I comment on that?
Shortly.
So yeah, of course, we can additionally also encounter the equilibrium position. However, I would still state that also, for example, our trends above our parameters are still fitting with our experiments and the numerical solution. So we can still make so we can still correct like that.
I don't really agree that this distance over frequency plot is really a good agreement. However, speaking of agreement, we can also move on to the agreement between your analytical theory and the trajectory of your plots.
Do you mean the phase, the free transformation?
The trajectory, not the FFT.
There's no.
You had a slide where you compared the.
This?
Yeah, exactly this
but
one.
There's no analytical theory. What?
Sorry, this was a mispronunciation. I mean the numerical theory. And as we can see, there are some discrepancies. And in our opinion, the task clearly states that we should investigate the motion. Thank you. The task clearly states that we should investigate the motion of the pendulum. In our opinion, your very high focus on frequencies does not cover the relevant motion of the pendulum in what we really need. What we need is this evolution of motion and how this evolution of motion is different throughout the phenomenon. Your frequencies are just averaged above the whole experiment, and I think that this is not sufficient. As you've shown, the most important mechanism of a magnetic Newton's cradle is the momentum of transfer from one side to another side. That's exactly what you also have shown in the beginning of your mode explanation. However, these modes don't really cover this. So I think this transfer of momentum, if you deflect one pendulum throughout this whole thing, is really relevant.
So first of all, I would strongly disagree on you that the frequencies and so on are not describing the motion. So as I always stated,
I have to interrupt here. I am sorry about that. Time is over. Thank you very much for the discussion. And now we head straight into jury questions, and Endre wants to start.
Okay, can you please go back to slide 44?
44, yeah, sure.
There you discarded the friction matrix. And my question, you stated that the friction is not relevant for the eigenfrequencies. Can you comment on that? Is this true also for the damped harmonic oscillator, for example?
So approximately yes. So of course there would be some very small deviations in the frequencies. However, I would state that generally we can say that this is a very good approximation, and it's also needed for solving our frequencies analytically.
Follow-up questions. What's your opinion?
Well, of course, the friction might be important. We can just imagine putting a pendulum in a tank full of honey where it is really decelerated, and then, of course, its eigenfrequency decays. However, I think in this setup, the friction is so less that for the analytical theory and the real physical understanding of the phenomenon, the friction is negligible.
Okay, I think Ilya had a question.
I have an experimental and a theoretical question. The experimental question is, did you experiment with this device, or did you also vary the length?
No, of course not. This is just a model of that. I used a much more complex and abundant experimental setup.
Yeah.
I also showed you. Would you like to see the picture again?
Yes, while I think about my other question. And the opponent didn't like your qualitative explanation with the modes. Regarding that, are you sure that you may talk about modes before you did a linearization?
Can you please?
Okay, you said that you have modes that superimpose.
Yeah.
Are you sure this is allowed to use this concept for a nonlinear system?
For a nonlinear system, so do you mean that? So I showed you a linearized superposition equation, which is made of several cosines.
Yes, but
of course, that is not completely true for our for the real setup, since due to the magnetic interaction, there is no perfect cosines. If that answers your question.
Okay. More.
There's just a simplification due to for the.
Okay. More questions? Yes, Thomas.
Thank you for this great fight to both of you. To the presenter, an important part in your theory is the modeling of the dipole-dipole interaction for the magnetic interaction. And therefore you use a far-field approximation, and you said citing maybe for a short time when the magnets move very close, it might be violated. Can you elaborate on this a little bit?
So for my numerical theory, I used the Biot-Savart law, which is still, which is also a very good, still a very good model for the near fields. I only used the dipole approximation, which is only the case for the far fields. Good approximation for the analytical solution.
Mm-hmm. Thanks.
Okay, maybe one more question. Okay, then Endre again.
To the opponent, you criticized the normal modes approach to for the characterization of the movement. What would you rather do?
So what we see is that if we deflect one pendulum, there's a wave propagation throughout this whole phenomenon. This wave propagates back and forth, and this is something entirely not covered by this report. And in my opinion, the thing that really is the thing that we have to compare between the cradle, the normal Newton's cradle, and this magnetic Newton's cradle. What he does is the edge case of the...
Thank you very much for your explanation. Now it's time for grading. Now all the marks are done, so we are now ready for the result, and we start with the result for the reporter. So please hold it up, and we have 9, 9, 9, 8, 8, 8, 10, 10, 9, 9, 9. Excellent result. Correction, one night was an 8, so 1 point down. Still, very good result. And the result for the opponent, we have, hold it up please, 8, 8, 9, 8, 9, 9, 9, 9, 9, 9, and another 9. So, also very good result. To give some feedback to the reporter, let's start with some of the lower marks. So maybe Elke, you can comment on your 8.
Okay. To the presenter, thank you for your really sophisticated, based explanation of the phenomenon. But what I missed is the thing that is also talked about in the opposition, that you focused mainly on your mode observation. And this is one description possibility, but I think for me also it's missing the more detailed observation of the other phenomena of the movement.
Mm-hmm. Thank you. Sami, maybe you can continue directly and comment on your 10.
Sure. You really caught me at the beginning. There are two words in the task this time that are not really defined by itself. Similar and other interesting. And with your presentation, you showed me, you really explained what do you mean by similar and what did you think was interesting. You were focused on the frequencies. You thought that was interesting and changed between those two cradles. And I loved it. I loved it that you structured your whole presentation based on this comparison. And thank you for that.
Okay. Yeah, so for the opposition, we were pretty uniform. So anyone who wants to give some feedback can. Would be nice to hear 2 jurors again. So Endre?
Maybe to the opponent, why I gave you an 8, or one reason, is so normal modes are a typical way to describe this. This is also a full picture for the linearized case. And what I was looking forward to is how, in my question, how would you then characterize if you go to the nonlinear regime? And this was very, I mean, we ran out of time as well. But I was lacking a little bit idea, okay, how to do this. There are, in literature, also ways to go beyond linearization, but they are very technically, and it goes fastly to numerics, and then you're just talking about numerics.
Okay. One more comment. Maybe Angela, can you comment on the opposition?
Thank you very much for your nice discussion. I really liked the discussion and I gave the 9 because there are only minor points to be discussed. And I gave the 9 and not the 10 because I think the discussion structure could be a little bit more following up, but this was the only thing I had.
Okay, thank you very much. And thank you to both teams for this really excellent second fight. It was really a pleasure to watch it. So now again, we have a very small break. This time, I think slightly longer. So we meet back at 11. Okay, thank you for returning on time to the very final match of this GYPT. Our jury is complete again. I think our teams are also complete and ready. So let's take a deep breath and start into the last match of today. Coming. So we have Alan Straniak from team Inu in Nürnberg presenting problem number 2, electrical damping. I think that's one of the probably all of us have seen, but probably not in your version. So we are very looking forward to that. And the discussion is going to be by Nikita Petrov from team Absolute of X. And yeah, now we are looking forward to the last fight of today. Please start the preparation time.
Hello, my name is Hello, my name is Alan. I'm from the team in Nürnberg, and I'll be reporting on task 2, electrical damping. A magnet is suspended by a spring will display simple harmonic motion when displaced. If the magnet oscillates within a coil connected to a resistor, its motion will be damped. Investigate the factors that affect the damping. In this short demo video, you see our coil in which the magnet is oscillating connected to a plastic rod and a spring driving the oscillation. I'll start off with a qualitative overview of the phenomenon. And first off, if we have an open circuit, so we have no resistance attached, then we just have a simple damped harmonic oscillator. We can therefore just fit the spatial damping later on, but this is the case without with infinite resistance, sorry. However, as we add the coil, we can observe some interesting further phenomena. Let's observe the oscillation from the start of the peak amplitude. On the bottom left, you can see qualitative voltage over position diagrams. On the bottom right, force over position diagrams. Now, as the magnet is at the top of the oscillation, it stops moving for a short amount of time, and the flux change within the coil is 0. Therefore, there is no induced current, no induced voltage, no induced current, and therefore also no magnetic damping force. However, as the magnet starts to move, somewhere in between the resting position and the peak, it reaches the strongest voltage induced as well as the strongest magnetic damping force. As it then reaches the center, though, the damping force as well as the voltage becomes 0. This is because the flux change above the magnet and below the magnet is exactly the same, just opposite, therefore cancelling out, so no current will be induced. As the magnet continues on downwards, we can see the same behavior as previously. This time, though, the voltage has changed polarity. The force is still pointing in the same direction, though. This is also indicated by the dotted lines you can see for the trajectories. And finally, as we reach the bottom of our oscillation, we stop again having the magnet stops again, having no induced voltage and no magnetic damping force. This behavior persists and is the driving phenomenon for the electrical damping task. Moving on to the quantitative model, we first have to determine the base oscillation we have without any resistance, so the driving oscillation in the phenomenon. This, we determine first of all the 2 spring constants as Hookean springs. These are 2 springs on the top and the bottom of the magnet. And additionally, we also have to determine the mass of the oscillating object. This is comprised of, on the one hand, of the mass of the magnet, however, also on the other hand, 1/3 of the mass of the individual springs, as the masses are comparable and cannot be neglected. For the spatial damping, we simply take a case, an open circuit, and fit a exponentially damped sine wave through the values to obtain our spatial damping coefficient. Now, in any given point in time, we have 3 main forces acting on our magnet. These are the spring force, the spatial damping force, as well as the magnetic damping force. Important to note, gravity here does not have an effect, as it will simply just shift the resting position. Now, these 3 forces can be written into this differential equation, and then rewritten into this ODE system comprised of the change in velocity and the change in position. To quantify the strength of the magnetic damping, we will first of all need to know how strong the current flowing through the coil is, for which we'll also need to, by my approach, calculate the voltage. We do this by applying the Lorentz force and integrate for each individual coil ring, and we'll then later sum them up for the entirety of the volume of the coil. Now it becomes apparent, since we use Lorentz law, that the only important coefficient or factor of the magnetic field is the Bx component, for which we can then use, and we can get this Bx component by using a Biot-Savart current cylinder approximation to obtain the Bx component at various different heights for a fixed radius of our coils. We can then fit the magnetization for our Biot-Savart to our magnets we use. We used a single thick and a series of 4 thin magnets for our experiments to obtain the magnetization for our theoretical comparisons. Now, going back to the electromotive force, we now have the Bx Biot-Savart equation. We can then sum up the individual contributions for the EMF for each single individual coil ring for the length and the width of the coil. These are indicated by the number of turns n as well as the number of layers m. We can now obtain the equation for the EMF and move on to the force. Now the force we calculate by taking the Lorentz force applied, since there is now current flowing through the coil, applied from the magnet to the individual coil, and then due to Newton's second law, the same force is therefore also applied to the magnet. So we can then sum up the individual coil contributions and obtain a relatively similar formula, but now this time for the force compared to the EMF signal. So now we have a total model which can describe our system, with which we can compare the experimental values with the theoretical values. Speaking of, let's move on to the experiments. First off, the experimental setup we used is of course comprised of a coil. This was attached to a breadboard for simple wiring, as well as a voltmeter for the EMF signal. And within the magnet we had, within the coil we had different magnets oscillating. These were comprised of the magnets attached to plastic rods to attach them to our dual spring setup, so we can limit the oscillations in Z dimension. Now, to obtain the position over time data, we used an OpenCV Python script for automated video tracking. Now, going on to the first preliminary experiment, in this case I've taken an open circuit and a coil distance of 1 millimeter. Coil distance is the variable I am using to declare the distance that the center of the coil has been shifted in regards to the resting position for our magnet. Since the circuit is open, the simulated force is 0. However, the EMF signal we can already see is asymmetrical. This is because the magnet during its oscillation period spends an asymmetric amount of time in the above the upper half compared to the lower half of the coil. Now we can also plot the EMF over distance diagrams and force over distance diagrams, and we see the same asymmetry over here for the first half period. Over time, the graph will look something like this. Now, as we add our resistance, we see the main difference being we now have a force, an electromagnetic damping force, which is induced. And therefore, we can also see this in the force over distance diagram. We can see the asymmetry as well, but most importantly, as the polarity of the voltage changes, the direction of the force does not. It always breaks the magnets during 1/2 oscillation, and then after this, it only shifts its direction. And finally, if we shift the coil distance a bit, we see a stronger asymmetry in the EMF and voltage signals, which we can also reflect in the distance diagrams on the top right and bottom right. Moving on to the parameter variation, we will be comparing the damping amount for various, for the most important parameters in the system. This is the amplitude drop in the first 60 seconds, so we compare the starting amplitude to the amplitude after 60 seconds and obtain how much % this has dropped by. Starting with the amount of coil layers, we can see in the characteristic distance and EMF diagrams for a 3-layer case and 1-layer case. They are relatively similar in both examples. However, the damping is slightly weaker in the 1-layer case, as we have less interactions between the magnet and the coil than in the 3-layer case. You can also see this on the right in the theory and experiment value comparison. Moving on to the coil distance, this is, I believe, the most important parameter, since when we are moving through, when the magnet is moving through the center of the coil, it is moving at its fastest if the coil distance is 0, because it's moving through its resting position. Now, if the coil distance is 0, this point is not being damped at all compared to other experiments, which is the most critical point, I would argue. And therefore, this small difference in not being damped will add up over time, leading to weaker damping for the signal over time. We can also see that these signals become more asymmetric in the EMF for a shifted coil distance compared to asymmetric case. Now moving on to the release position variation, we see that for small variations in the release position, we have pretty similar results in the damping amount. However, for larger release positions, there is a slightly weaker damping amount. This is mainly due to just the pathway, the energy being transferred to the coil at different positions and the optimum damping point and where it lies. Now, we wanted to verify our theory using comparing the two magnets we used just to verify the general applicability, because some models can still be applicable, for example, dipole, if they are fitted. This is not the case for us, so we wanted to verify this using a variation of magnets. And we can see that for both examples, we find a very close agreement between theory and experiments for the damping amount. And finally, we can vary also the resistors, and this is perhaps the most intuitive parameter variation, where if we have a stronger resistance, the current will be weaker flowing through the coil, therefore the electromagnetic damping will also be weaker. We'd also like to observe some further insights into the phenomenon. First of all, mainly the frequencies governing the system. Now, this is a simulation and the respective FFTs for the various components. And we see that the base frequency of the distance is apparent here from the spring oscillation. However, the EMF signal is double the frequency of ZFT. For coil distance 0, this is the case because as we are passing through the as the magnet is passing through the center of the coil, the polarity of the voltage changes once, which has to be accounted for and is therefore visible as a peak at the first harmonic. The force, though, is comprised of multiple frequencies, as this change in polarity, again, does not change the force's direction, only its amplitude for a short amount of time, and then only after the half period it will shift in direction. Now, if we shift the coil distance slightly, we see mainly that the EMF signal is now comprised of the frequency of ZFT in the first harmonic, as well as the force becoming a higher complexity signal. Furthermore, if we shift the initial position 7 centimeters in this case out, we see that the signals become vastly more peaky. This is because when the magnet comes into close proximity of the coil, the induced current and induced voltage will be much stronger, but for a much shorter amount of time. Therefore, these signals will be much more peaky, or will be much more pronounced with their peaks. Therefore, these signals are much more complex, and we can observe this also in spectrograms. For example, for the distance, we see that the base frequency persists for variation of the initial position. These are many simulations stacked after each other. But for the EMF and the force, the complexity will decrease as the initial position decreases because the signals are less peaky. Now, finally, observing the energy of the system, we have a decay of mechanical energy converted to mechanical friction over time and electromagnetic friction. Since our 4 thin magnets have a weak BX component and the thick one has a stronger one, we have a stronger EM friction amount here. And this increases as we increase the amount of coil layers as we have more interactions. Finally, we can also graph the electromagnetic friction over coil distance experiments, and we can find an optimum of around 1.1 centimeters numerically in this case. So in conclusion, we've built a sophisticated experimental setup to using OpenCV video tracking, have provided a theory based on Biot-Savart current cylinders for an approximation for our magnets, and found good correlation between our theory and experiments. Thank you for listening.
Thank you for the talk. Now 2 minutes preparation time.
hello, test. Awesome. So, yeah, I would be ready to begin. First of all, huge thanks for your presentation. I think it gives an awesome insight into the problem and has a lot of experimental as well as the theoretical insight. But nevertheless, I must ask you some questions. So I would like to start with the task interpretation. Maybe a small point, or just yet stay there. The task states that the magnet oscillates within a coil. And later on, you just introduce the coil displacement and so on. Do you think this is a relevant thing? Because the task states that the magnet should be within the coil.
Okay, so I think it's a rather open question in this regard. So, regards to, first of all, within a coil, in my experiments, the experiments actually were, due to geometrical constraints, always the magnets were physically inside of the coil. I think, though, you could argue that the within a coil part would mainly refer to the strong interactions around the coil. So being in close proximity to the coil is how I would define this, because the effect of the magnetic interaction will be there regardless.
Okay.
However, sorry if I could just add one thing, the change in, if you are moving outside of the coil, you will only have a positive or negative flux change, above or below the magnet, which is, so you won't have the voltage zero thing, which I showed later. So you could have a slightly different effect in that regard. So that would be an effect you wouldn't see if you're only oscillating outside of the coil.
But you answered my question. In most of your experiments, the magnet was within the coil, so you're basically fulfilling that part. Talking about the experiments, can we maybe just move to your part with experimental setup? Maybe we can just also stay here. That's all right?
Here?
Yeah, exactly. I have several questions. First of all, the coil, where the coil comes from. Is it you just bought it, or did you?
So in Bayreuth, we 3D printed the coil's core, and then we have an industrial coil winding machine which can very precisely wind the coils. So you have minimal errors in the coil's winding itself. There are still some imprecisions.
So you winded them yourself?
With a machine.
Okay, but do you have maybe measurements of the accuracy of the windings? Because I think if you're winding them themselves, some inaccuracies can be pretty decent.
No, I agree that they can be decent. I think this is also cause for some deviations in theory, but no, I don't have the measurements for those.
Okay, but so I would propose to measure, for example, just have a constant current onto the coil, and then with a magnetic field measurement, just go through the coil and measure the magnetic field. And just to make sure, for example, that at least on the axis it's just as the theory predicts.
I think that is a good...
Okay, so that would be my proposition. And second question, the starting. So I don't see any starting amplitude thing. Did you do it by hand?
We displace it by hand, and then we can just we displace it by hand. We invalidate the experiments where the oscillation is too large in x and y, of course. And then when the oscillation is in z direction, which is easier due to dual spring setup, we can then also take from the video data the initial displacement.
But during the parameter variation, did the starting amplitude was consistent?
Yes, because the comparative experiment was the same. Well, in some regards, it might have changed by a millimeter or two, but I showed in the one experiment that these very small changes won't have as large of an effect on the damping itself.
Okay, I would maybe slightly disagree with you because we could see that there is some dependency. So I would say that would be important to account for that. But you can just, I think, in your theory, maybe just for the one simulation, which are you comparing, just look at the initial conditions and then it should
I can maybe clarify my points, or do you want to move on?
Yeah, just let's move on.
Okay. Yeah.
Staying by the experimental setup, I think you've earlier mentioned that you used 2 different springs.
Yes.
Why use 2 different spring constants? Why not just the same ones?
It was just due to the springs we had on hand. We only designed this, and it wasn't changed during the experiment. I think there is no fundamental difference, though, when you use 2 same springs compared to 2 different springs.
Okay, I wouldn't really agree with you then. I think there could be some nonlinearity or some strange effects which could come with using 2 different springs, and I think just using 2 same spring isn't that much of a problem, and that would simplify the whole problem.
Okay, I can agree with the simplification part, but I don't agree with the nonlinear effects due to, if we can look at Hooke's law, it's dependent on the displacement, and the displacement relative to each spring is the same relative to the resting position, meaning that k times x can just be, the 2 k spring components can just be added up.
Okay, yeah, I agree with you on that point. Okay. Looking at the magnets here, for your theory, you use Biot-Savart approximation.
Yes.
So the uniformly load to the magnetic cylinder. And for that, to have a comparison with the experiment, you need some kind of value for the magnetization. Did you use a literature value?
No.
Did you measure it yourself?
So what we did is we took, sorry, where is the slide? 1 second. So we took, I could just draw it maybe. So we had the magnet, which was fixed at z distance. Yep. We then comparative to the center, we then fixed our Hall probe to 2 centimeters radius, because this is the coil radius we used for our coils. And then we went along the Z direction to obtain values for the magnetic field. Oh, sorry.
Do you have maybe a plot of the foot?
This is the plot. So then we have the magnetic values for the Z component, and we can then fit the magnetization to this.
Did you make sure that the magnetization of the permanent magnet is also right?
If it's axial?
Yeah.
No, in this case not, and I think this is also a cause for deviations in our theory, a possible cause at least.
And was that measured for a single magnet or for the whole bench of the stacked ones?
So it was, for the single thick, for the one magnet, it was measured for only this magnet, and then for the 4 thin magnets, we considered this being as one thick, one stacked magnet, being as one unit, and then we just basically we did the same thing, just that the...
I understand, so you just measured it.
You just measured it.
Okay, so I would disagree with you. I would think it would be important to measure and make sure that the magnetic field of the couple, or just to get magnets put together, is also homogeneous, because if we have a slight difference in the magnetization of the single magnets, which could be just caused by the production or something like this, the overall magnetic field could be a bit unhomogeneous, especially in the near field, and I would say the near field also plays a huge role in this phenomenon. So moving on from that, I would say it would be important to make sure that... Okay, but thank you very much. Moving on, you didn't, in your theory, maybe can you show the electromagnetic force? I think if we look there, you didn't really account for the inductance of the coil, or the self-inductance, I mean.
Yeah, because I think the frequencies we are operating at are way too low for this.
The frequencies, but I think the self-inductance itself is there, so we have an RI circuits, like the resistor and an inductor circuit.
I guess you could see this, but again, I think also the voltages we're operating at are very small compared to this. Okay, I think this could have been accounted for, but I don't think it will be it will create a massive difference or will account for the deviations we see in theory and experiment.
Okay, but I would disagree with you, because I think the inductance of the coil would just have a particular phase shift in the inducted voltage, and this is an important thing to compare later on, because this is a direct thing which affects the dampening.
Okay, that's your point.
Then let's move on to your variation of the parameters, to the slide 34.
Yes.
And here you're talking about the dampening amount to quantify the dampening process. Do you think this is an accurate or a right scale to compare different parameters? Or to just quantify the dampening happening in the system?
So I think for quantification of dampening, there's various approaches I've seen and heard of, for example. There's some based on the energy in the system. I think this would probably be the most applicable. Observing how the electromagnetic friction, effectively how I called it, would develop over time and then cutting it off at some point. I think the 60 seconds, they are to some degree applicable because my experiments are rather long, they take 2 or more minutes to fully dampen out. However, I think what you're talking about is after a specific amount of time in the beginning, the main dampening force will no longer be the electromagnetic damping. Okay.
So my point would be that for me 60 seconds looks like a huge time period, and if we are trying to take an account only the electromagnetic dampening or just to quantify it, it doesn't really make sense to take this huge amount, because then we have a huge part of the mechanical dampening in the part, because from a particular time the amplitude is just too low, and so there isn't much inducted anymore. And as a result, I think 60 seconds can just average out the results if you have that much of mechanical dampening.
Well, I will kind of disagree with you still. Yes, the mechanical damping will be stronger after the time period, but if you're observing exponentially damped systems, if you have the same time scale.
The problem that this is not an exponential damped system.
I want to argue what my point is by using an exponential damped system. So if you observe an exponential curve and you take a look at some kind of period in time, the percentage drop will be the same, meaning that the component dampened by the spatial damping, since it is exponential, will always have the same effect after 60 seconds, meaning that the difference will be mainly caused by the EM damping.
I think the main problem here that we are not talking about the linear dampening. We have a highly non-linear dampening happening in the system.
I agree.
And as a result, I would say this isn't really accountable, and because of that, but okay, just move on. Okay. Do you have maybe an idea how we can separate the electromagnetic dampening happening in the system from the mechanical one?
I guess we could subtract the like an uncoupled case from like without a resistor, for example, and then we could just like have the amplitude behavior based on the electromagnetic
I
damping.
understand. I think like a much more precise way would be looking at the dissipated energies happening in the system.
As
So
I
you can
mentioned
just look
previously.
at your voltage and, for example, just look how the anticipated electrical energy
it
leaves
curves
the
over
system,
time.
and then you can do the same with the dampening constant and the velocities and see the mechanical. And as a result, you would have a perfect separation. And I think it would be also very relevant for the dampening amount, because then you can see the region where the electromagnetical dampening has the most effect, and then this would be the right part, in my opinion, to quantify the phenomenon.
Okay, I agree. I think this is a good improvement idea for the future.
Okay, awesome. So maybe then we'll move on to your FFTs analysis. And I would
Yes.
just like to ask, which insights do they give us into the phenomenon?
Okay, so I mainly just wanted to talk about this. If you have like a extremely strongly dampened system, you can sometimes have shifts in the frequency. I just wanted to show that this is not the
Okay,
case in my
so
experiments
there is no-
for the base frequency. And for like more asymmetric cases, you can have a high complexity in the voltage and the force signal.
But do this all single harmonics tell us something about the dampening itself? Can we just derive something from that, or it just shows the complexity of the dampening happening?
Mainly, I just wanted to show like how the complexities behave and which components of the dampening are prevalent
Okay,
here.
I get, but I would say that this is not that much relevant to the task, and this may be, yeah, you just show it, but it doesn't really show us much insight into the dampening process itself. But okay,
okay,
well,
yeah.
So, and maybe the last parameter, the parameters of the system, how would you, okay, we don't have any time more. So then just let's sum up. In this discussion, we went over the task interpretation, and then we agreed that the parameter wasn't very relevant, that it's moving within. Then we discussed a lot about the experimental setup with some possible inaccuracies of the happening problems and of the springs, and also the measurement of the magnetic dipole moment or the magnetization of the magnets to the applicable. And then we discussed most of the time the dampening amount and how it is applicable for the problem with the coefficient or as the quantification of the dampening. So huge thanks for the discussion, and yeah, thank you.
Thank you also on my side for this great discussion. Now we head straight into jury questions. Who wants to start? Yeah, Angela.
To the opponent, you criticized that there are two different springs, different in spring constant, and I think as well in the mass. What do you think is the effect of the different mass on the experiment?
So the mass directly affects the theory which we're using, but you mean the mass of the springs? Maybe because they're positioned on top of each other, they could be or should be accounted for in the theory, and that would be some influence.
Thank you.
Then Endre?
And to the presenter, how did you account for the effective mass, so combined?
So like in the beginning, I showed, sorry, let me just find it. Okay, so we have basically, if we assume linear mass distribution along the springs, we can integrate a small portion of the kinetic energy components along the springs, and then if we integrate this, we can get
Yeah,
1/3.
Thank you. Next question, Antonia.
Yes, if we could go back to, for example, slide 40, my question in general would be, we saw the damping amounts always like in these colored boxes as like these values. Do you have an idea what your uncertainties around them are, and do these trends align in general? Because I have to be honest, like during your presentation, I didn't completely pick up on how well they match.
Yeah, sometimes, in some cases, they did not match as well. I think this is due to maybe for smaller differences, the mass of the oscillating mass being slightly off, but I don't think this is the main cause. I think the main cause would be imprecisions in the coil windings, which is I think that Nikita's idea would be good to account for this, as well as sometimes the coil possibly being slightly angled, therefore the dampening being weaker. But I don't have current statistical significance on the variation of the damping strength, since my setup relies on hand displacement, and for this I would still want to have the same amount of displacement, which I currently don't have.
Okay. Yeah, Ilya?
Yeah, probably to the opponent, you said that it's not exponential. Can you name some special conditions under which the amplitude would decrease exponentially?
So only the mechanical dampening would be the case, so just like open circuit?
Yes.
That would be the case.
That's not interesting. And with electricity?
I think if we have a very long coil, then we would have near no electrical dampening, and due to that we would also have an exponential decay due to mechanical. But I wouldn't say that if we have an electrical dampening in the system, I wouldn't say that we would have a possibility to have the exponential decay here.
Okay.
Okay.
And do you think there is a possibility?
I think I would agree. I think, again, the mechanical decay being the main component here.
Do we have another question? Yeah, Endre.
Sorry, to the presenter. You showed us mostly the case where the oscillation is in the middle, as centered around the middle of the coil. Why did you not look at, why did you not concentrate on longer coils and on oscillations above, so at the edge where you would find much more damping?
So I have actually measured an example for the coil distance variation. Maybe I can find it. Okay, so I'll comment on this. So I have measured this. It's stronger for coil distances above 0 in my case. And for longer coils, there were some problems during manufacturing when we were making the coils, so that the resistance between the coil and the rest of the circuit, I fitted it just to test how large it would be. It was around 80 ohms. So I wanted to disregard this, as I didn't think this would be significant.
Thank you very much for this round of questions. Now we head into the grading, and for that I have a remark. We have now the special situation that Nikita worked on the same problem as Alan, and one could argue that that gives him a slight advantage. So the grading will be done as usual, so the jurors just pick their grades as usual, but later, when calculating the final grade of the team, there will be 1 point deducted for your opposition. So keep that in mind when we present the marks, that there is this adjustment later on. Okay, when I observed correctly, the last mark is made. So we can head into the presentation of the results. So we will again start with the results for the reporter. So please present your mark and hold it up. Now we have 7, 8, 8, 8, 7, 8, 9, 8, 9, 9, and 10. Okay. And for the discussion, please prepare your marks, hold them up. Now we have 9, 8, 9, 9, 9, technical difficulties, 10, 10, 10, 10, 10, and 10. Amazing. What a score. So let's give some feedback, and let's start with the report, and maybe Endre can start.
Yeah, I would like to start. I would like to comment on my low grade to the presenter. I think you made a nice job, okay? So this is also cool that you fabricated your own coil and so on, but there were some parameters missing, in my opinion. And you also didn't consider some of the interesting physics behind, so time dependence of, for example, the damping. You didn't show us modelings of experimental theory modelings of the damping, for example, but just showed us the numbers, but not in the graph and compared to curves that you could get out of your theory. Okay, so this was a comprehensive theory, but for me, a lot of interesting physics was missing, unfortunately. Okay.
Okay, and then Angela for the 10.
Okay, so I gave the 10, and main points are that I was impressed about the basic explanation and the very sophisticated experimental setup with the 2 springs. And another big point was that was your part of the discussion.
Okay, thank you very much. And discussion is the right word, so we will head into your feedback, and maybe Ilya, you can comment on your 8.
Well, if everyone gives 10, it would be too homogeneous. No, yes, the points that have been said in critically to the reporter, I think you could have pushed it more, that he didn't show a graph that shows the 1/r dependence that we expect and such things. And yeah, and maybe you used the blackboard more also.
Okay, thank you. Jonas, would you be willing to comment on your 10?
Yeah, I think this was one of the best oppositions I saw in this competition, and I think it was a real scientific conversation. So for me, it was a 10.
Okay, thank you very much. And with that, we conclude the fights for this GYPT. Thank you, everyone, for this amazing discussion. Big round of applause to everyone. And now we have the last break before the opening ceremony starts, and we meet again here at the closing ceremony. Sorry. Sign error here. And we meet again 5 minutes to 12, right? Okay, see you then.
Genau, Preisverleihung. Gleich geht's los. Wir haben ganz tolle, wichtige Personen eingeladen als Lautatorinnen und Lautatoren. Mir war gerade noch wichtig, weil heute ist Internationaler Frauentag und jetzt hatten wir auf der Bühne gerade nur Männer gesehen. Wir hatten aber beim Bundeswettbewerb 1/3 Frauen und ich finde, das ist für einen Physikwettbewerb echt gut. Genau, wer eben schon mitgerechnet hat, weiß vielleicht schon, wer Silber und Gold bekommt. Was ihr aber noch nicht wisst, ist, wer Bronze bekommt. Und die Bronzemedaillen, das sind im Teamranking aus der Vorrunde die Plätze 4 bis 6. Die verteilt der Herr Dr. Stefan Jorda von der Wilhelm und Else Heraeus Stiftung. Ohne die Förderung von der Stiftung wäre dieser ganze Wettbewerb und unsere Teilnahme an den internationalen Wettbewerben gar nicht möglich. Vielen Dank, dass Sie da sind.
Auch wenn wir hinter der Zeit sind, ein paar Minuten müsst ihr mir geben, bevor ich die Bronzemedaillen verleihe. Ich bin, glaube ich, seit 2016 immer beim GYPT dabei gewesen. Ich war die letzten Jahre als Vertreter der Stiftung und als Juror. Ich war die letzten Jahre beeindruckt. Ich bin auch dieses Jahr wieder super beeindruckt, nicht nur von den Fights, die wir jetzt gesehen haben, sondern auch von den Fights, die ich gestern gesehen habe. Jede von euch hat ganz Tolles geleistet. Ich bin auch beeindruckt davon, was über die Jahre entstanden ist. Aus diesem kleinen Pflänzchen GYPT sind mehr und mehr Standorte dazugekommen. Es sind mehr und mehr Betreuer, es sind mehr und mehr Teilnehmer. Ich finde es klasse, wie viele ehemalige Teilnehmer inzwischen sich engagieren an den Standorten als Juroren, als Betreuer und so weiter. Für uns als Stiftung ist es ohne Zweifel ein Aushängeschild, ein Leuchtturm. Wir fördern diesen Wettbewerb mit rund 250.000 € jedes Jahr. Das ist nicht nur für hier, das ist natürlich, da ist das GYPT-Team mit dabei, da sind Personalkosten drin, Betreuertreffen an den Standorten und so weiter und so fort. Und ich bin davon überzeugt, dass jeder einzelne Euro davon sehr gut investiert ist. Wir haben jetzt in 4 Wochen Gremiensitzungen und die DPG hat einen Antrag eingereicht für die nächsten 3 Jahre, also 3 mal 250.000, kann man sich vorstellen, was da rauskommt. Wird sogar ein bisschen mehr. Nächstes Jahr geht es nach Neuseeland, da gehen die Reisekosten ein bisschen hoch. Aber ich glaube, ich hänge mich jetzt hier nicht zu weit aus dem Fenster, wenn ich sage, dass ich überhaupt keinen Zweifel daran habe, dass wir diesen Wettbewerb natürlich weiter fördern werden. Geld ist wichtig, aber mit Geld allein kommt man auch nicht weit. Deswegen möchte ich auch im Namen der Stiftung all denjenigen danken, die diesen Wettbewerb möglich machen. Das ist natürlich zunächst hier das Team, das Orga-Team rund um dich, Liane, und Diana Carstensen, die heute leider nicht dabei sein kann, die Unterstützung aus der DPG-Geschäftsstelle, all die ehemaligen, die sich hier um Technik, Fotos kümmern, die Betreuer vor Ort und alle weitere, die dazu beitragen. Ganz herzlichen Dank dafür. So, jetzt kommen wir aber zu den Bronzemedaillen. Also eine Bronzemedaille mit 46,17 Punkte bekommt das Team Piper aus Hameln mit Phil Peters und Erik Stefan Vanzelow. Foto gibt es jetzt oder zusammen? Okay. Genau, wenn ihr gerade wartet aufs Foto. Dann das mit 46,31 Punkten Team Hell aus Lörrach. Philipp Adelbrecht, Max Stiefel und Quirin Zimek. So, wenn ihr auch gerade drüben wartet, gleich gibt es dann ein Foto. So, und schließlich mit 48,5 Punkten das Team The Cricket Union Berlin-Charlottenburg, Unisens, Harikan Tulapati und Ivan Zaitsev.
So, für die Silber- und Goldmedaillen, wie gesagt, wer vorhin live mitgerechnet hat, weiß vielleicht schon, wer welche Medaille bekommt. Trotzdem ist natürlich die Zeremonie wichtig. Ich freue mich ganz besonders, dass Frau Dr. Heike Riel heute da ist, gestern noch aus den USA eingeflogen, extra nur für euch. Sie ist... Genau, sie ist eigentlich sowieso zu früh da, weil sie ist erst ab April die Präsidentin der Deutschen Physikalischen Gesellschaft, aber natürlich schon gewählt. Trotzdem schön, dass Sie hier sind.
Vielen Dank. Ja, also erstmal einen ganz herzlichen Dank, dass ich heute dabei sein darf und gestern Abend auch schon die Stimmung mitnehmen durfte. Es ist wirklich ein super spannender Sonntagmorgen für mich gewesen, hier zu sehen, was hier alles passiert ist, dieses Finale mitzuerleben und hier dabei zu sein. Spannende Physik, tolle Erklärungen, interessante Diskussionen, Fights, wie man auch gehört hat, spannender Austausch von starken Argumenten, tolle Erklärungen, Passion, Energie. Das ist eigentlich wirklich toll gewesen, das alles zu sehen. So eben wie Physik sein soll. Dafür wirklich einen ganz herzlichen Dank. Ihr alle habt hier tolles Leben in die Bude gebracht. Es war wirklich toll zu sehen. Mir ist es gestern sofort aufgefallen, als ich hier am Abend reinkam. Ich bin ja auch öfter hier im Haus der TBG, aber die Veranstaltungen, zu denen ich war sozusagen typischerweise nicht so energiegeladen und so wuselig und wirklich tolle Stimmung, als ihr hier hergebracht habt. Also dafür ein ganz, ganz besonderer Dank an euch alle. Und dass der GYPT-Wettbewerb Bundeswettbewerb sozusagen wieder hier im Physikzentrum stattfindet, passt natürlich namentlich. Ja? Das Zentrum, die Physik steht im Zentrum. Und genau dieses Haus ist ja eben auch für uns, für die Deutsche Physikalische Gesellschaft, sowie das Wohnzimmer der Physik. Und dahin gehört Physik. Und ihr habt sie auch hier wieder reingebracht. Ihr habt sie in die Flure, in die Räume gebracht. Alles vibrierend, inspirierend, wirklich voller Energie und Passion. Und ihr habt sozusagen hier das Haus der Physik wirklich mit Physik gefüllt. Wirklich toll gemacht. Ich hoffe, ihr hattet auch alle tollen Spaß, Freude, Energie, Austausch und habt viel gelernt. Und was dazu gehört, gerade bei diesem Event, auch habt euch kennengelernt, habt euch vernetzt und habt miteinander gearbeitet, denn diese Verbindungen, die bleiben auch bestehen und daraus entstehen Freundschaften, die auch in Zukunft bei euch bleiben. Ich bin natürlich auch allen dankbar, die zu dieser Veranstaltung beigetragen haben, die das ermöglicht haben, nicht nur jetzt während der letzten 2 Tage, sondern auch die ganzen Vorbereitungen, die natürlich da auch wichtig waren. Und dass auch wir hier im Physikzentrum eben, dass dieser Event stattfinden konnte. Also da ein ganz herzlicher Dank an viele verschiedene Menschen. Ein großer Dank an die Koordinatoren des Koordinatorenteams der Universität Ulm, aber auch natürlich an die Geschäftsstelle der DPG, die nicht nur jetzt am Wochenende, sondern über das ganze Jahr hinweg diesen Event und diese Veranstaltung sozusagen darum kümmern, auch um die verschiedenen Standorte sich kümmern. Das ist ein Teil, insbesondere natürlich auch Diana Brandt und auch die Frau Carstensen und auch der Michael Steck, der jetzt auch da nochmal dabei geholfen hat, es möglich zu machen. Und aber, das hat der Stefan Jorda vergessen, natürlich an die Heraeus-Stiftung ein ganz großer Dank, weil die Heraeus-Stiftung mit dem Stefan Jorda er hat es ja auch anklingen lassen, dass dieser Event nur möglich ist, natürlich mit der finanziellen Unterstützung. Und wir alle sind da wirklich sehr dankbar, denn hier entstehen Talente, hier sind brillante Forscher für die Zukunft, die sozusagen auch dann die Physik in die Zukunft tragen. Und Stefan Jorda, wie wir gehört haben, er ist ja nicht nur sozusagen körperlich anwesend, sondern eben auch enorm tatkräftig unterstützt er diesen Event und dafür auch an dich persönlich ein ganz großer Dank. Das Physikzentrum zeichnet sich auch aus durch die tollen Personen, die hier dafür sorgen, dass wir auch unser Leib und Wohl hier gesorgt ist, dass wir hier sein dürfen, dass alles passt und deshalb auch insbesondere hier an den Dirk Gutiran und auch den Viktor Goma ein großer Dank, die das natürlich auch immer dafür sorgen, dass es uns hier gut geht. Was ich gestern Abend auch vor allem in den Begegnungen erfahren durfte, ist eben auch die Superleistung der Lehrer, der Mentoren, der Mentoren und Mentorinnen, der StandortleiterInnen und der Hiwis, der Ehrenamtlichen, die hier mit viel, der Seniorprofessoren, die hier mit viel Herzblut und mit Passion und Energie wirklich dafür sorgen, dass hier ein toller Event und tolle Leistungen und wirklich sehr, sehr professionell gearbeitet wird. Also auch da ein ganz, ganz großer Dank an diese ehrenamtliche Arbeit, ohne die wir hier nicht auch die Physik so fördern könnten, wie das getan wird. Danke, ein ganz großer Dank. Also im Prinzip an alle ein einfaches Weiter so, mit viel Energie und viel Kraft vorwärts. Denn im Juli kommt ja auch schon der nächste Schritt, der internationale Wettbewerb, der International Young Physicists Tournament, was jetzt dieses Mal in Zürich stattfinden wird. Es wird an der ETH stattfinden, habe ich gesehen, in den ETH-Räumen. Und da wird man sozusagen nicht nur viel mitbekommen von der ETH, von dem Flair, auch von den ehemaligen Absolventen und Lehrern wie Einstein und wie auch Pauli und vielen anderen, die auch in diesen Hallen sozusagen auch waren. Deshalb hoffe ich, dass ihr alle sozusagen ja, mit Energie und Passion euch dazu entschließen werde, dahin zu gehen und hier einen spannenden Wettbewerb und auch uns als Physik in Deutschland hier die Fahne für die deutsche Physik und für den German Wettbewerb auch hochhalten werdet. Das wird sicher spannend, sich dann auch mit den internationalen Peers sozusagen zu messen und hier auch weiter zu lernen und weiter dabei zu sein. Die ETH hat sicher ein tolles Programm auch zusammengestellt und ich habe mir jetzt heute Morgen überlegt, da ich ja nicht weit entfernt von der ETH arbeite, und da doch dann ein paar Kollegen aus dem Gremium hier dann in die Schweiz kommen, dachte ich, ich komme mit einem kleinen Bonbon und einer kleinen Überraschung, dass die sozusagen Deutschland da vertreten werden, ich sehr gerne, sobald so die Zeit erlaubt von der Seite der Gäste, auch bei mir gerne im Labor empfangen würde und da hier auch einen kleinen Einblick in unser Labor geben würde. Deshalb wünsche ich erstmal weiterhin wirklich viel Erfolg und wir kommen jetzt dann auch zu den spannenden Namen, die in diesem Umschlag sind. Genau. Ich kann sozusagen direkt loslegen. Genau, Sie sehen hier, die Silbermedaillen werden verliehen an das Team in Nürnberg. Benjamin Graf. Genau, das sind wir. Wow. Benjamin Graf, Elisa Schöpf und Alan. Ja, einen herzlichen Glückwunsch an euch. Ihr habt das super gemacht und deshalb gibt es jetzt auch hier diese Silbermedaillen. Ich darf mal mit der Dame anfangen. Einen herzlichen Glückwunsch. Lesen. Ja, okay. Mit 24,99 Punkten an Mihailo Markesic, Nikita Petrov und Ayush Yadav. Einen herzlichen Applaus. Glückwunsch. Genau, und jetzt kommt natürlich ganz spannend, viele haben es schon erraten, die Goldmedaille. Und auch hier einen ganz herzlichen Glückwunsch an Till Cooney und Jonathan Oswald. Einen herzlichen Glückwunsch. Toll gemacht.
Dann vielen Dank, Frau Dr. Riel. In diesem Jahr zum ersten Mal wird der Preis in Gedenken an Ottmar Winkler für die beste Diskussion im Bundeswettbewerb vergeben. Ottmar Winkler war ein GYPTler der ersten Stunde beim allerersten Wettbewerb schon dabei, genau, und ist letztes Jahr tödlich verunglückt. Und die Idee, einen Preis in seinem Namen zu vergeben, kam tatsächlich von den ganzen anderen Lehrkräften, die für das GYPT engagiert sind. Genau, und dafür lade ich Anja Speth nach vorne für die Laudatio. Anja Speth ist Vorstandsmitglied in der DBG für den Bereich Schule und ich denke, das ist für einen Wettbewerb für Schülerinnen und Schüler und wo auch ganz viele Lehrkräfte anwesend sind, natürlich sehr passend. Vielen Dank, dass Sie da sind. Dankeschön.
Ja, ich darf nun die GYPT-Auszeichnung für die beste Diskussion in der Vorrunde in Gedenken an Ottmar Winkler verteilen. Das tue ich mit einem lachenden und einem weinenden Auge. Einem weinenden Auge, denn Ottmar Winkler, mit dem an diesen Preis erinnert werden soll, der fehlt. Er fehlt in der DPG, unter anderem bei uns im Arbeitskreis Schule, wo ich ihn kurz kennenlernen konnte, aber er fehlt auch hier beim GYPT-Wettbewerb. Überaus engagiert hat er sich ehrenamtlich in diesem Wettbewerb eingesetzt, beispielsweise als Juror hier vor Ort, aber auch seit 2014 als Leiter des GYPT-Stützpunkts in Meißen. In dieser Funktion begleitete er immer wieder Schülerinnen und Schüler über den Unterricht hinaus und begeisterte sie für die Physik, animierte sie zu Höchstleistungen. So wurden dann auch einige der von ihm betreuten Jugendlichen Teil des Nationalteams. Letztes Jahr gewann das deutsche GYPT-Team, begleitet und unterstützt von Ottmar Winkler, in Schweden die Goldmedaille. Kurz darauf ist er bei dem tragischen Unfall ums Leben gekommen. Aber ich vergebe den Preis ja auch mit einem lachenden Auge. Denn auch in diesem Jahr gab es unglaublich tolle Fights hier unter Ihnen, kreative Lösungen und unkonventionelle Lösungen, die zum Staunen angeregt haben. Und ich bin sicher, Ottmar Winkler hätte sich sehr über die Diskussionen in der Vorrunde auch gefreut. Und damit freue ich mich nun, die Leistung auszeichnen zu dürfen. Mit 9 Punkten in der Vorrunde geht dieser Preis an Herrn Nikita Petrov aus Dachau.
Du hast ein bisschen schlecht. Vielen Dank, Anja Speth. Genau, wir haben es schon fast geschafft, was jetzt aber noch ganz, ganz spannend ist, das weiß auch noch niemand von euch, oder doch, Ottmar Marti weiß es tatsächlich schon. Seniorprofessor Ottmar Marti ist auch, glaube ich, seit der ersten Stunde beim GYPT dabei, Professor an der Universität Ulm, die den GYPT wissenschaftlich koordiniert. Ich selbst bin auch an der Universität Ulm. Genau, danke, dass Sie da sind.
Ja, bevor ich hier die Namen verlese, möchte ich kurz sagen, ich freue mich, dass die Universität Ulm das zweite Heim des GYPT sein darf, neben hier Bad Honnef. Und ich bedanke mich bei der Deutschen Forschungsgesellschaft, bei der Hereo-Stiftung für die Unterstützung dabei. Die Universität Ulm ist relativ klein, hat Physik, vorwiegend in Quantenphysik und in Biophysik, und das war es jetzt auch schon. Also, ja.
Ich muss Sie ganz kurz unterbrechen, und zwar es wurde uns vorher schon gesagt, dass 2 Personen nicht am Auswahlworkshop teilnehmen möchten, sofern sie denn reinkommen. Und ich möchte sie aber trotzdem nennen, weil sie ganz weit oben waren bei den Punkten. Die beiden wären qualifiziert für den Auswahlworkshop, kommen leider nicht, weil sie sich fürs Abitur vorbereiten wollen. Genau, aber ich möchte bitte einmal Applaus für die beiden, für Benjamin und Alan.
Ich weiß zwar, dass es nicht stimmt, aber ich wünsche den beiden das Äquivalent von 10 Punkten in ihrem Abitur. Soll ich oben oder unten? Naja, einfach von oben. Also Workshop mit Teilnehmerinnen und Teilnehmern, die schon eine Medaille bekommen haben. Mit 26,4 Punkten Herr Jonathan Oswald. Dann mit 26 Punkten Nikita Petrov. Dann mit 24,77 Punkten Herr Philipp Adelbrecht aus Lörrach, Dachau und auch Lörrach. Dann mit 24,33 Punkten Herr Younes Senz, Berlin-Charlottenburg. Mit 23,67 Punkten Herr Phil Peters, Hammeln. Mit 23,5 Punkten Herr Ivan Zaitsev, Berlin-Charlottenburg. Mit 22,6 Punkten Herr Ayush Yadav, Dachau. Mit 22,5 Punkten Herr Erik Stefan Banselow, Hameln. Mit 22,4 Punkten Frau Elisa Schöps, Bayreuth. Und jetzt gibt es noch 3 Personen, die keine Medaillen bekommen haben, aber persönlich trotzdem in diesen Punkterängen drin sind. Das ist mit 23,3 Punkten Herr Karim Rachidi, Papenburg. Mit 24,51 Punkten Herr Linus Konnert, Berlin-Charlottenburg. Und mit 25,94 Punkten Herrn Philipp Klippel, Dachau. Herzliche Glückwünsche an alle. Herzlichen Glückwunsch.
Okay, damit haben wir es im Großen und Ganzen geschafft. Vielen Dank, Herr Ottmar-Marti. Noch ein paar letzte Punkte zum Schluss. Die 12 Workshop-Teilnehmenden, das sind übrigens diejenigen, das haben wir noch gar nicht so richtig gesagt, die sich für die Nationalteams, die zum IYPT in Zürich, haben wir gerade gehört, waren und zum AYPT, der Europameisterschaft nach Leoben. Und die werden mit dem netten Kerle da oben reisen, das ist das Maskottchen von den internationalen Teams, das ist schon länger beim GYPT als ich und reist immer zu allen Wettbewerben mit, er heißt Horst. Genau, und die 12 Workshop-Teilnehmenden, wir treffen uns gleich im Anschluss oben, wo gestern Matchraum E und F war und dort wird für euch auch Essen serviert. Die BetreuerInnen, StandortleiterInnen, die können gerne mitkommen. Genau, und ihr könnt auch gerne schon anfangen zu essen, ihr müsst nicht auf mich warten. Das ist letztes Jahr schiefgegangen, deswegen sage ich das lieber. Genau, alle anderen, da hinten wurde schon auf magische Weise gerade die Pinnwände entfernt, vielleicht habt ihr es gesehen. Da liegen für alle anderen Teilnehmenden die Teilnahmeurkunden. Nehmt euch bitte eure Urkunden weg. Außerdem gibt es noch jede Menge Poster für das kommende Wettbewerbsjahr 2027, packt ihr euch bitte auch ein. Und ihr bekommt Essen wie die letzten Tage im Lichtenberg-Keller. Ab ca. 14 Uhr, ihr kriegt dazu dann auch noch mal eine Mail, werden eure Ergebnisse, also die von den Teilnehmenden, die Jury hat schon ihre Ergebnisse bekommen, unter dem folgenden Link, wie gesagt, den kriegt ihr auch noch mal per Mail geschickt dann. Und damit ist der 13. GYPT-Bundeswettbewerb geschlossen. Dann gute Heimreise.